Hello there guys, welcome back to another epic inexorable maths video. In this video we're doing a little bit more work on matrices, and we've got two very special types of matrix to look at today. So the first one that we're going to look at is an identity matrix. So these are really important types of matrices, and I've written on here kind of what they are. So an identity matrix is a matrix that is always a square matrix, okay? So it has to have the same number of rows as it does columns, okay? And in general, an n by n identity matrix, which you can write as IN, and again, it's only being underlined because that's the notation that I tend to use. Normally people write matrices in bold on a computer, but if you're writing with chalk or with a pen or a pencil, you can't really make things bold very easily. So I just underline instead. So this just means that it's a matrix. That's what the underlining is. So IN, I with a little n there, means the n by n identity matrix. Now what is it? It is simply going to be a matrix that consists of all zeros except on what we call the leading diagonal, which is the top left to the bottom right diagonal. You have the number 1 going all the way down. So for instance, the 2 by 2 identity matrix would look like this, 1, 0, 0, 1. You see, it's all zeros, but on the leading diagonal you have ones. The three-dimensional identity matrix would look like this. It's all zeros, but on the leading diagonal you have ones, okay? And this would work for any number that you want. The 4 by 4 identity matrix would look the same, all zeros, but it would have 1, 1, 1, 1 going down the diagonal. That's what they are. Now, why is it important? Well, the identity matrix has a very special property that when you multiply it by any matrix of the same dimension as it, it leaves the matrix alone. So for example, if you had something like the matrix 1, 2, 3, 4, and if we multiply that by the identity matrix, and of course we're going to do the 2D identity matrix, 1, 0, 0, 1, what's going to happen? Well, it's going to give you back the matrix that you started with. So if we actually do this and check that that's true, we're going to do 1 times 1, which is 1, plus 2 times 0, that's just 0. Next entry, 1 times 0, that's 0, plus 2 times 1, so 2. Bottom left, 3 times 1, plus 4 times 0, so 3. And finally, 3 times 0, which is 0, plus 4 times 1, which is 4. And you see it's given us back what we started with. And even though matrix multiplication is not commutative, which again, commutative means that you can do one operation one way around and it will work the same as if you do it the other way around. Matrix multiplication is not commutative, which means matrix A times matrix B will not necessarily equal matrix B times matrix A. Even though that is true, if we were to do this the other way around, watch what happens. So I'm going to do the same thing, but I'm going to swap the matrices around. So 1 times 1 is 1, plus 0 times 3, so just 1. 1 times 2, 0 times 4, so 2. And as you're seeing, we are actually getting the same thing again. So it doesn't even matter which way around you multiply the identity matrix. So what, mathematically, for any matrix A, oh, the chalk's just halved. That doesn't matter, that's fine. For any matrix A, and we'll say that A is a 2 by 2 matrix right now, okay? So it's a 2 by 2 matrix, but it could have any numbers in it, it could have whatever you want. For any 2 by 2 matrix A, we have the A times the identity matrix, and again, I'm not going to write I2 because it's 2 by 2. You don't have to write the 2 down there if it's clear what the dimension is. A times the identity matrix is just A again. And the identity matrix times A is just A again. So this is kind of mathematically what we're looking at. Now I said this is for 2 by 2 matrices. However, as long as A and I are square matrices of the same dimension, so as long as they're both 2 by 2, they're both 3 by 3, they're both 4 by 4, etc., then this will always work. This is kind of the definition of an identity matrix. And it's called the identity matrix Because this is what you would call the multiplicative identity element for a square matrix. What that means, that's a bunch of word salad basically, right? But what it means is take any matrix you want, times by the identity, you would just get your own matrix back. That's why it's called the identity matrix, okay? So you can times any matrix by the identity matrix, or you can times the identity matrix by any matrix, either way, and you would just get the one that you started with back. So this is kind of like the matrix equivalent of timesing by the number 1, right? It's the same kind of vibe. Now let's look at a zero matrix. So a zero matrix is arguably even simpler of a concept, because all a zero matrix is any matrix of any dimension where every single element, every single entry to the matrix is just the number 0. So for example, you could have a zero matrix that looks like this. That's a 2 by 2 zero matrix. You could have a zero matrix that looks like this. It's not a square matrix, it can still be a zero matrix. This is a 2 by 3 zero matrix, etc., etc. That's what a zero matrix is. And a zero matrix is, you could call it the additive identity to a matrix, because as you can, I mean, it's quite obvious that if you take any matrix, let's say we have the matrix A again, this time matrix A is going to be an M, I'm going to call it an M by N matrix, okay? So it's going to have M rows and N columns, okay? It's an arbitrary matrix of any, it doesn't have to be square, just anything. This plus a zero matrix, which I will just call 0, like it's just 0 underlined, or in bold if it's in a textbook. Again, this would be the M by N. This is an M by N zero matrix, okay? So they have to be of the exact same dimension. So if this is a 3 by 2 matrix, then this needs to be a 3 by 2 matrix as well, because that's the only way that you can add matrices. They have to have the same dimensions. Then this would just equal the matrix A again. And just like with the identity, it's commutative, because matrix addition is commutative. So 0 plus A would still just be A again. We're now going to finish off the video with an example question that's going to involve identity matrices or matrices, and how exactly we're going to deal with those. So the question is, we get given a matrix A that has, it's a 2 by 2 matrix, and the elements are 3, P, minus 4, Q, and we get told that A squared, so just A times A, is the identity matrix. And again, it's implied that this is the 2 by 2 identity matrix, because it's a 2 by 2 matrix. We're only dealing with 2 by 2s here, so it wouldn't be a 3 by 3, right? So it's implied that this is I2, okay? You don't need to write it. And the question is to find the values of P and Q. So maybe pause the video, have a think about what you might do in order to work this out. But if you're not sure, we're going to go through it right now together, and let's see what happens. So we get told that A squared is the identity matrix. So why don't we use that to write an equation? First of all, let's work out what A squared is. So A squared, of course, that's just the matrix A times itself, which is going to be 3P minus 4Q multiplied by 3P minus 4Q. And let's see what that's equal to. So 3 times 3 is 9, plus P times minus 4 is minus 4P. Okay. Then 3 times P is 3P, plus P times Q is PQ. So 3P plus PQ. Okay. Bottom left, minus 4 times 3 is minus 12. Plus Q times minus 4 is minus 4Q. And then minus 4 times P is minus 4P. And Q times Q is Q squared, so plus Q squared. Okay, so that is what we've got so far for A squared. I'm just going to rub this out so we have a tiny bit more space here. And what we want to do is we want to set this equal to the 2 by 2 identity matrix, which we know is 1, 0, 0, 1. And now what you can do, guys, with this is that you can literally just read off. We have 4 different equations that we can read off, and we can use that to find the value of P and Q. So if we look at the top left equation, which says that 9 minus 4p equals 1, we can get the value of P. So 9 minus 4p equals 1. Okay? That means that if we take 1 away from both sides and add 4p to both sides, we are going to have that 4p equals 8, which means that p is the number 2. Okay? Hopefully that makes sense. Doing the exact same thing with another one, we can choose. Which one's the simplest? Probably the bottom left one, because that only has q in it. So if in the odd chance we got p wrong for some reason, both of these ones here, top right and bottom right, they both have p in them, so maybe we'll stay away from that. Why don't we use the bottom left? But it's personal choice. Bottom left equation says that minus 12 minus 4q is equal to 0, because minus 12 minus 4q equals 0. Okay, so if we add 12 to both sides, we will have minus 4q equals 12. Divide both sides by minus 4, we will have that q is equal to negative 3. So where should I write the answer? The answer is that p is 2 and q is negative 3. Okay, and that's all there is to it. If you were in an exam or something and you wanted to check your answer in some way, then of course you could go back into A, replace P with 2, replace Q with minus 3, literally square it and check that you get the identity matrix. And you could even substitute 2 and minus 3 into the top right and bottom right entries of the matrix to make sure that they're equal to 0 and 1 respectively. Okay, so there's lots of ways to check your answers. But that's how you do a question like this involving an identity and 0 matrices. As always, guys, I highly appreciate you watching the video. Thank you so much for watching, and I'll see you in the next one. Cheers.